Hello, students. Welcome to the subject Cryptography and Network Security. Where in Module 2, the next session is about elliptic curve cryptography. In the previous session, we have seen the elliptic curve Diffie-Hellman key exchange, how a secret key gets exchanged between the two parties involved in the communication through an insecure channel. Now, in this particular session, let us talk about the encryption and decryption process supported by the elliptic curve cryptography. So, as we have seen, elliptic curve cryptography, it's a public key cryptographic system, right? So, which makes use of two different keys for two different purposes. So, the fact here is elliptic curve cryptography does not rely on large prime numbers like how RSA was, but it basically makes use of the mathematics of electric curve over a finite field, right? So, as I told, or as we have seen in the previous case, even the keys of small size would give us a stronger security. I just had given a simple comparison of RSA and ECC in the previous video, right? So when it comes to encryption and decryption, how does ECC help us? So let's see what are the steps involved. We have to select the domain parameters, which would basically would be same as what we have seen in the elliptic curve Diffie Hellman key exchange, and about the generating key pairs also. And we are mainly concentrating on encryption and decryption. Right, let's see what is the first step involved. Selecting the domain parameters. So when I say domain parameter, selecting domain parameters, you know that we have selected the elliptic curve using the parameters a, b, and q, where q is a prime number, right? So this prime number, or it is any number which is of the order 2 power m, right? This is what q is. If it is not a prime number, it should be of this order. And then you are going to select a point G on the curve, whose value should be as large as the value n. And what is this n? This is the restriction that we are imposing on us. So an infinite field, but we are restricting ourselves to finite field, and that finite value is n, right? And then that is what is this, the size of finite field. As I mentioned earlier in the previous video, it can be 256, 384, anything. The best value that we can take is 256 bit. It's not that only we have to. It's not that we have to only take 256. No, it is a reasonable, because it provides a greater security compared to the, in comparison with the RSA of a greater size, right? And generating key. So here basically both the user will pick a private key. So let's consider the private key as D, which is a random integer, right? Again, this random integer, when I say random integer, this random number can be generated, right? We have seen Blum-Shub generator, linear congruential generators. So using any one of those technique, we could generate this D, right? And based on the value of D, a public key Q will be calculated, right? How it is calculated? Q is nothing but D into G, right? So say, consider if I have A and B as the two users, then let's say DA is the private key of A, and let's say DB is the private key of B. Now, how what DA does, what A does is it will multiply its private key with that base point G, which would give QA and QB. Let's consider that this QA and this QB is the public key. Right? So you have the private key in the form of DA and DB for A and B, and public key in the form of QA, QB. Now we are very well set to perform the encryption process. So say, consider I have A wishing to send a message to B. Right? A wants to send a message to B. We have source A and we have source B. It wants to send the message, and it is trying to make use of cryptography for sending the message, right? So we know, when we are talking about encryption and decryption, we are mainly talking about confidentiality, right? We will talk about confidentiality when we talk about encryption and decryption. So what actually A does is, A takes a message, right? A takes a message and it encodes that message into point M on the curve. Now, this message, which is maybe a text message, but now this text message is converted into a point on the elliptic curve. Okay, so this you have to remember. Also, what A does is it chooses a random integer k and it computes two parameters. One is C1 and another one is C2. So this C1 and C2 together they form the ciphertext. C1 and C2 together they form the ciphertext. Now, how is this ciphertext obtained? So, as I told, we are going to combine this C1 and C2. So, what is C1 here? C1 is nothing but this integer k multiplied by the point g. C1 is nothing but k into g. What is this C2? Which is the next part of the ciphertext. See, when we say ciphertext, it should contain the message, right? But in part 1, there's no message. So in part 2, we have this message combined with the k multiplied with the public key of B, right? So we know encryption, decryption, while providing confidentiality, we have to make use of public key of the receiver. So where that came into picture? Here in part 2. Now these two are combined in the form of a point. We are talking about curve, no, elliptic curve. So we have to send it as a point, right? So in that point, as you know, in a two-dimensional space, we will have two dimensions to represent a point. So here, let's say consider C1 acts as x-axis value and C2 acts as y-axis value. Well, let us consider like that because we are considering point, right? So now C1, how it is calculated, the random number chosen multiplied by G, and C2 message, to which we are going to append the K multiplied by that public key of the receiver. Now this message would be sent on the insecure channel. As you know, it is cryptography being used. So what happens? Basically, the message is hidden, right? Now, B will receive what? B would receive this ciphertext, which is in the form of a point C1 and C2. Now, B will use its private key to calculate DB, right? So, before it computes the plain text message, what it does is, so it in the step one, it is going to consider that x value. When I say x value, it is C1. It is going to take its private key and it is going to perform this point multiplication, db multiplied by c1. Once this is done, in step 2 what it does is it would subtract this particular value which is calculated in step 1 from the y-axis value. That is, it is going to perform c2 minus db into c1. This is what it's going to perform. Now when this step is completed, you are going to get that message back. When this is only, there are two steps, right? For the first step, x parameter is considered. It is multiplied with the private key. As you know, private key should be used, no, by the receiver to decrypt the message. So how this decryption is done? So this new parameter, new value that is calculated, it is subtracted from y value. Let's see how we get message m, right? So we have this, what is that, c2 minus db into c1, right? So in encryption, we know what is C2 and what is CD. C2 is nothing but your M plus K into QB, correct? Right? Yes. And what is C1? C1 is nothing but K into G. K into G. Okay. So now this is M plus K into QB. You know that point multiplication is associative, closure, commutative. It satisfies these properties. Can I write this as K multiplied by DB multiplied by G? Obviously. Now, what is this value? Private key of B multiplied by global point or the base point. So it is nothing but QB. Right. K into QB minus K into QB. Now I can see that this and this get cancelled. So what is that I'm going to get? I'm going to get M. So that is how decryption is being performed. Right. So the here the ciphertext is sent as a pair of value because we are considering point on the curve. So we have to divide it like this. So hope it's clear. To summarize, what elliptic cryptography does is, so if in one of the videos earlier, we have seen that ECC can be used for providing the encryption, decryption, the key exchange, the digital signature, right? Yes. So ECC involves selecting the curve parameters, which is nothing but the step one, generating private and public key, step 2, and that is how it is generated through the point multiplication. Here point multiplication is used only to generate public key, private key is selected randomly, right? And then key exchanging. So key exchanging can be done if it is only used for key exchanging purpose, or if it is used for encryption and decryption, we can use that also, along with digital signature, right? It provides that support also, digital signatures, right? And what I can say is, its efficiency and smaller key size makes it ideal for mobile devices, IoT, and modern internet security. So, with this, we have come to the end of elliptic curve cryptography. Thank you, students.